Feels weird lecturing to only 3 people. Like I feel bad for keeping you guys here. Oh, if I was alone, I'd literally just load up the videos and say, don't shut up, I'm leaving. Did I hit record? I did hit record, okay. So we got math 21. We're doing 6.1, which is on.
It's too bright.
I see that. Thank you. How about that? Is that bright enough? And I can see.
Now it's too dark.
I know, I'm trying to get it to fix. Just that grid right there. All right, so math 21, chapter 6, we're doing 6.1 and 6.2 today. 6.1 is on discrete random variables. In fact, all of chapter 6 is on discrete random variables. Oftentimes, we don't have all the data, but a summary. Normally, we could figure out like the mean pretty quickly. Is that where I want to start? I feel like I'm starting in the wrong spot. And when we have that, we can make a table and do discrete random variables. So let's talk about what discrete random variables are. I'm going to abbreviate random variables as RB. The important stat crunch things today and formulas you're going to need from this section. So the expected value, this is a formula that we're going to use, and you're going to need to know it. It's not in stat crunch. It goes by E of X. It's the sum of X times P of X. E of X also goes by mu of X because it's the mean. For stat crunch, we're going to do stats, calculators, and then custom. So those are the end game things you're going to need to know, or things you're going to use. Now we just got to talk about what each individual component is. So I keep mentioning random variables here. Random variables are numerical measures of the outcome from a probability experiment. we tend to write it as probability that big X equals little x. Where big X, or the capital X, is our categories, the category of outcomes. Like what are we talking about here? If we're talking about rolling a die, it's what the die roll. And the lowercase x, the small x, are the individual outcomes. And we kind of want to have all the individual outcomes for when we do the random variable table, as you'll see. Give everyone a second to write this down. All right. Not all right. You all right? You good now?
Yes.
So I think maybe giving you a specific example is going to be more helpful than just saying big shit. So let's say Linda and I play rock, paper, scissors. And I want to measure my number of wins. Times I win out of, let's say 5 games. So if I want to write that in the notation of like probability of big X equals little x, I need to kind of address them, what they are. So big X will be the number of times I win. That's what I'm keeping track of. That's what I care about. Little x are all the possible outcomes. Little x can equal 0, 1, 2, 3, 4, or 5. Those are the outcomes in that scenario. So like if we were doing like best of 5, I want to win more, 3 or more, right? I would write this as the probability that the big X is greater than or equal to 3. So this is kind of like saying, what is the probability that the number of times I win is greater than 3? the number of times I win is actually what I called the big X up there. This is my random variable. It's random because it could take on the values of 0, 1, 2, 3, 4, or 5. Let me pause for a second. They call this a discrete model. This is a discrete probability model. Discrete means it can only take, the values can only be whole numbers. Or countable numbers. When we have stuff that isn't whole numbers, like in between, like that tends to be when we're working with continuous data, and that will be chapter 7. Everybody have a chance to write this down. All good? So let's look like a scenario like, so like a, those are probabilities, a probability distribution. This pin is dead. I'm getting a new pin. Isn't a whole lot better, is it? So probability distributions, these are tables listing all possible outcomes. And their probability. So we're going to look at the number of movies, for example, streamed from Netflix in a month. And these are definitely pre-pandemic numbers because that shit skyrocketed during the pandemic. And we haven't really gave that up yet. Zero, 1, 2, 3, 4, and 5. do the probability that X equals 0. It was 0.06. Someone's got their microphone on. Probability that X equals 1 is 0.58. And I'll just fill out the table and give you guys a chance to copy it. Hearing shit. Right. All right, so note here. Notice that all the probabilities are less than 0 or less than 1. They're also all bigger than 0. This is a rule. It's our rule. So all probabilities have to be at least 0 and less than 1. And if I call that rule A, rule B is that if I add up all the probabilities, it has to add up to 1. These are the 2 requirements for a probability distribution model. So for all of these things, we like to find the mean. The mean of the random variable X. It's going to be the sum of X times P of X. We can calculate this by hand, and then we'll do it in StatCrunch. I wish I'd given myself more room on the right here, because this would have been a lot easier. I could have just done it on the same fucking table, but I didn't. So I'm going to relist the X and P of X. And I'm just going to show the values for now. Just copying those values down. And I'm going to make a third column, and I'm going to do X times P of X. So 0 times 0.06 equals 0. One times 0.58 is 0.58. Two times 0.22 is 0.44. Three times 0.10 is 0.30. Four times 0.03 is 0.12. Finally, 5 times basically a penny is 5 pennies. And if I sum these all up, I get 1.49. And we're talking about movies per month. Clearly pre-pandemic. Now, this is just summarized data. This is summarized data. If I had a list of all the people they used, if I had a list of households and how many movies they watched, list of households and how many movies they watched, I would just find the mean the normal way. So this is like the actual data, or when I get the actual results, these are like the actual data. And this is more like the theoretical. Which means, so like if the household, if we had n households and houses, as n gets really large, I was using mu of x for the mean here. The mean on actual data is like x bar. As n gets really large, the x bar, the sample mean, gets close to the actual theoretical mean. Or another way of looking at that is like x minus mu of x goes to 0, or is approximately 0 as n gets really large. And that actually has a name. This is called the law of large numbers. It's really, really important. As the sample size gets really large, we get more, the sample gets close to the actual mean, the theoretical mean of what it should be. Now, if you watch the videos for chapter 5.1 through 3, and I talked about Past the Pigs, they had like some like 10,000 fucking pig tosses or some shit like that. That's a large number. And adding just one more doesn't really change the results. Short term though, no, can't count on this short term. Whoa. Start moving shit around, Jones. So this mu of x is not reliable short term. And I'll show you. In my next example on roulette. I'm only gonna do 6.1 today. 6.2 goes better with 6.3. And 7.1 goes better with 7.2. I don't know why I split it the way I did on that. So that was a dumb split. Does anybody not know what roulette is? Have you guys ever seen roulette?
I've seen it.
You guys aren't old enough to have played it legally. They're fucking back there like, yeah, I know what roulette is. You ain't gotta tell me. Let's talk about roulette then. In fact, let's bring a picture up of roulette. Because I can't guarantee everybody that the home viewing audience knows what I'm talking about. That's a good picture. So roulette, casino game. They spin the wheel one direction, like it might be going clockwise, and they flick a white ball, a marble, going counterclockwise the other direction. I don't know which direction they spin, but I know they go opposite directions. So eventually the friction causes the white ball to slow down, and it's like tilted inwards. So as it slows down, it eventually falls into the center. It lands into a hole in one of these right here. Oh, this is a single off table. The Remember that each slot is numbered and colored. There are 36 slots normally, and then there's normally 2 green slots, a 0 and a double 0. So maybe I should find one that's got that.
Americans.
Fucking the roulette experts back there. There we go. That worked. All right, so 0 and double 0 are called ought and double ought. Ought is another name for 0. So there's several ways you can bet. You can bet on any particular number by placing your chips on that number only. You can bet on any 2 numbers by placing the chips on the intersection of those 2 squares. You can bet on any 4 squares by placing on the where those all meet. You can do a 6-pack if you do it at the edge. Like if I place it right here, the 1 and 4, like the chip on the 1 and 4, it's covering the numbers 1, 2, 3, 4, 5, 6. That's not every casino, but some casinos have it. They have bets on whether or not you can bet on strictly even or odd. You can bet on red or black. And these pay 1-to-1, red, black, even, odd, whatever you bet. If you get it, you win it, that amount. The ones that are, if you pick a group of numbers like 1 to 12, 13 to 24, 25 to 36, you're betting on any of those 12 numbers coming out. It pays 1 to 2. You only get 1 for every 2 that you bet. No, other way around. Yeah, other way around. You get 2 for every 1 that you bet. Because you have less than half the numbers available to your choice. You can also bet on the first half and the last half right here. You can also bet, another way to bet on 12, rather than betting on a box like this, you can bet on a row by putting your money down here. And finally, there's the 2 things that make it so that the casino has the edge, 0 and double 0. The better game is the single 0 game. The probability that you come out ahead is, sorry, let me rephrase this. The probability that the casino comes out ahead, because they do come out ahead no matter what, is always lower for a single 0 game. So, like, how does this shit work? Let's take a look at one of the bets. So we got a roulette. It's got 36 slots and then 0 and double 0. Which means there are 38 numbers total. So if you bet on a single number, it pays $35 to 1. You bet $1, you win $35 if it hits that number. Not bad. It doesn't hit that often when you bet on one number. Linda, what's your favorite number between 1 and 36?
Let's go with 7.
7. All right, so Herlinda bets on 7. With 35 to 1 odds. We're going to come up with the probability distribution model here and figure out what the mean value is. So if the ball hits the 7 is one outcome. Or the ball misses the 7. I'll do the miss in green. So if we're looking at make the random variable how much she wins. If the ball hits, she wins $35. And if the ball misses, she loses $1. Oh, switching to green. And what is the probability of X? Well, for the ball to hit a 7, there's only one slot that has a 7, and there's 38 slots. So the probability of hitting the X is 1/38, which is about 0.0263. The ball misses 7 is every other outcome. If we've only got one that's a 7, that means 38 minus 1 or 37 outcomes is everything else. 37/38 is about 0.9737. And I meant to do that in green, and I'm not doing green, so I fucked it up. So if I do X times P of X here, I have $35 times 1/38. And I'm going to get 92 cents. If I do the one for ball misses, I've got -1 times 37/38. And that's -97 cents. So if I add these up, sum of X times P of X is -5 cents. On average, in the long run, for every dollar you bet on roulette, you lose a nickel. Notice nickel is not one of the outcomes. She can either win $35 or lose 1. So oftentimes these average outcomes are not even possible outcomes. That doesn't seem like a lot. Most people don't bet $1 when they play. They bet $5, $10, $20, something like that. If she played or someone plays, a total of $10,000. Every one of those dollars is going to have an expected loss of a nickel. 10,000 times 0.05, negative 0.05 is negative $500. It adds up. The scenario I did right here was her picking a single number, 7. The magic that is roulette and the way they did the betting, it doesn't matter what bet you fucking take. Even or odd, betting on a single number, betting on a row of 12, the expected value remains the same. The average loss is always a nickel for every dollar. 4, when there is 0 and 00, this required, the problem is the 35 to 1 accounted for the 36 numbers. The extra 0 and 00 are what give the house the edge. So if you like playing roulette, roulette is fun. You're better off playing a single 0 table. They have them even in America. They tend to be the higher stakes tables. They don't want you sitting down with $1. They want you playing $100. Because their edge is lower. It's like 0.26 or some shit like that. 0.026. So for them to make money and pay for the dealer and stuff like that, they want, more bets. How do I do this in StatCrunch? Let's take a look. Guys, oh, Herlinda's right. Let me let's wait for it. Let me get StatCrunch over. Are you done?
Yeah.
So what I'm going to do is I'm going to label one of these columns at the top as X, and one of them is P of X. We'll put the 35 and the -1 in here. And it won't do the fraction, so I got to put in the decimals here. 0.0263. Number lock is off. Son of a bitch. So we are going to do, once you have the table in, you need to have the table in. Some of the homework problems, you can just, it'll upload the table for you, which is good. You want to go to stats, calculators, custom. All of these are alphabetical except custom. Custom's at the bottom. The values are your X and your weights are your P of X. That's all it is. If you've got the table in, you say where the values are and where the probabilities are, X and P of X, and you click compute. And it tells me the mean right there. And so it looks like I was wrong. I rounded when I said a nickel. It's really negative 0.0532, So if I were to bet 10,000, I would lose $532 on average. This is never an individual outcome. It's the result of a lot of plays. If you just go and bet 10,000 in one single toss, you're either winning or you're losing. You're gonna win a lot or you're gonna lose a lot. 532 is not an option. So this is the result of long-term play. We got one more example we're gonna do and then we'll be done. Any questions so far? So I'm gonna go over here and rewrite that custom bit. So it's in the written lecture notes real quick. In SC, have the table in. Preferably with columns labeled. X and P of X. Use stats, calculators, custom. When it asks you for values, you tell it where X is. And when it asks you where the weights are, you tell it P of X. Shit, Sebastian's not even here. What is this? Maybe. Smart little fucking Doogie Housers and shit, right? I think I'm smart, but I didn't do that shit. Of course, he's probably clean as a whistle. When I was his age, I was doing drugs and stuff. So I didn't like want to go to college. I just wanted to get high after school. All right. Next example is term life insurance policies. And I'm going to throw out this black pen too. And I don't have an extra black pen. So we are doing red, blue, and green for the rest of the day. A lady pays $530 annually for life insurance. I'm going to abbreviate life insurance, INS, for insurance. And the life insurance with coverage of $250,000. The probability of survival a woman her age survival for the year, just the 1 year of the insurance, is 0.99791. And we are going to compute the expected value for the company. The only person that really cares here. Like from the lady's perspective, she pays for it. When she dies, she don't see that money. It helps her family, but she's not gonna see it. But it impacts the business or the company every time. So we want to make a table of outcomes. Expected value for the company must be related to how much money, right? That's what's of value to the company, how much money. So we're going to be looking at money in terms of our X's. What are the two outcomes in this scenario?
Either the lady has to select the use money, or she doesn't, we can take. Premium.
She lives or she dies, right? And so if X is what the money portion. If she lives, they gain $530. What does it cost them if she loses? You would think this was a trap. They do lose the $250,000, but she's already paid that insurance. So they already have the $530. So they really only lose $250,000 minus the $530. They get to keep the $530. And so if we do that, you're going to get negative $249,470. What's my P of X here? If the woman survives, it says it's 0.99791. They don't ever tell me the probability of her dying, though. How can I get the probability of her dying? We're going to use that, but how? It may be worth remembering that the sum of probabilities have to equal 1, which means that the probability she lives plus the probability that she dies has to equal 1. And I know the probability of her living. So if I subtract the 0.99791, I'm just left with the probability that she dies is 0.00209. I made $560 this week for 4 hours of work for a casino. Just doing this probability shit. Good money. Good if you know what you're doing, if you're good at it. That's good money for 4 hours of work. Sitting on your ass? What?
Lost 1,000 trying to do that.
I wasn't, I was designing or helping them fine tune their bets. Their payouts for their bets. They want to make sure they had a certain amount of income. And then they have to walk a very fine line. You don't want to make it so that you rob the fucking customer blind, even though they want to. If you rob them blind, they leave and they don't come back. So you have to rob them blind slowly.
You think like every game's rigged?
Every game, it's not rigged, but the probability of you winning is lower than the probability of them winning. Blackjack is generally like the closest it gets, and that's with perfect play.
And Baccarat.
Baccarat's pretty good. We got some gambling degenerates in here. I love it. We're not done with that table. I got all excited talking about degenerates. So now I just got to multiply. If I multiply 530 times that, I get plus $528.89. And if I multiply these, I get negative $521.39. And if I add these up, that's $7.50. The company can expect to make $7.50 insurance contract. That's not a lot of money, is it? Especially when you pay out is $250,000, right? The thing is, they don't just do it with like 10 customers or 100 customers or even 1,000 customers. If you had 1 million customers, several of them are going to die. You're going to have to pay out a lot of 250,000, but you are collecting that 530 on a lot of them. And so 1 million times that $7.50, 7.5 million ducats. So insurance companies, casinos, stuff like that, they're not playing the short game, they're playing the long game. Because when they lose, they generally have to pay out a lot. But they don't lose that often. And I'm going to come over here and edit StatCrunch. If everyone's ready, we'll take a look at it over here. Rather than making new columns, I'm just going to use the old columns, but I'll put in the information we had. We had 530 was one of the values. And negative 249,470. Don't use commas. StatCrunch doesn't like commas, neither does MATLAB. The probability for the top row was 0.99791. And the bottom row was 0.00209. stats, calculators, custom. We tell it where our X's are, we tell it where our P of X is. And it does all the work, and the number you're looking for is the mean. The mean is 7.5 or $7.50. And that's all I got. So we'll do 6.2 and 6.3 on Thursday, 7.1 and 7.2 next Tuesday. Thursday, we'll have a review in class, and then the following Tuesday will be our test. 2 weeks from now. It is coming by pretty fast, isn't it? Anyone online have any questions? If not, that's it.
Bye, have a good night.
You too.